All right, today we're going to dive into a principle that's hiding in plain sight in everything from the click of your pen to the insane thrill of a bungee jump. We're talking about Hooke's Law. We're going to unravel its secrets, from the simple formula to some pretty mind-blowing applications, so you'll have everything you need to absolutely master this core concept.
So what really connects something as boring as a ballpoint pen to something as terrifying as a bungee jump? Well, it turns out it's a surprisingly simple law that governs the springiness of pretty much everything around us. Way back in the 17th century, a guy named Robert Hooke summed up his big discovery with this elegant Latin phrase. And it's this incredibly simple but really profound idea. The more you stretch something, the more it fights back. If you double the stretch, you double the force. It's a rule that just makes sense, but it's also incredibly powerful. Okay, so let's take that simple idea and translate it into the language of physics, right? The formula F equals kx is your key. It unlocks the power of Hooke's law. And we're going to break it down piece by piece so you can avoid all the common mistakes. And here it is, the golden rule. F equals kx. F is the force you're putting in. K is, well, let's call it the spring's unique personality. And x is how much it stretches. This one little equation is the secret to everything from designing safer cars all the way to acing your physics exam. Okay, listen up, because this is so important. We need to talk about x. This is, without a doubt, the single biggest place people make mistakes. X is not the final length of the spring. It is the change in length from where it started, from its natural resting position. So if you have a 10-centimeter spring and you stretch it to 12 centimeters, X is just 2 centimeters. And please, 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 always convert centimeters to meters before you do any math. Get this right, and you're honestly halfway there. So what about K, the spring constant? Well, think of K as the spring's personality, seriously. A really high K value, that means a super stiff spring, like in a car's suspension. You need a massive force just to compress it a little bit. On the other hand, a low K value is a loose, floppy spring, like the one in a pen or a slinky. A tiny little force and you get a huge stretch. It's a direct measure of stiffness. All right, now for a classic exam trap. You're going to see this formula written two ways, with and without a negative sign. So what's the deal? Which one is right? Well, they both are. They just describe two completely different forces. F equals kx is the applied force. That's the force you exert on the spring. F equals negative kx is the restoring force. That's the force the spring exerts back on you. That little minus sign just tells us the spring's force is always trying to pull back to the start in the opposite direction of the stretch. They're a perfect action-reaction pair. Okay, so we've got the formula down. Now let's see how this all looks visually. Because a force extension graph, it's not just a line on a page. It's a whole story that reveals all of a spring's secrets, from how stiff it is to just how much energy it's holding. Because F equals kx is what we call a linear equation, its graph is just a perfect, beautiful straight line right through the origin. It's the visual signature, really, that tells you Hooke's law is being obeyed. No force, no stretch. Simple as that. And here's the first secret that this graph tells us. The gradient, the rise over run, is literally the spring constant, K. It's that simple. And this makes it so easy to see stiffness. A really steep line means a big gradient, which means a big K, a very stiff spring. A shallow line? Well, that's a much looser spring. Okay, secret number 2. And this one is about energy. All that work you do stretching the spring, it doesn't just disappear. It gets stored up as potential energy. And the amount of that energy? It's the area under the line. You can think of it like a visual energy bank. So let's see how we can pull the energy formula right out of this graph. It's actually super simple. The area is a triangle, right? And we all know the area of a triangle is 1/2 times base times height. Well, in our case, the base is the extension, x, and the height is the force, F. So energy equals 1/2 Fx. But wait, we also know that F equals kx, so we just swap that in and boom, we got our final super useful formula. Elastic potential energy equals 1/2 kx squared. Now, that little squared in the formula, that is a huge deal. It means the relationship isn't linear anymore. If you double the stretch, you don't just get double the energy, you get 4 times the energy. This is exactly why you can overstretch a rubber band just a tiny bit more, and it'll snap back with a surprising amount of force. But what happens when you push things too far? Hooke's law is an amazing guide, but like any rule, it has its limits.
Let's talk about the breaking point, the moment where the rules of the game completely change.
Think about stretching a material as a journey. At first, everything's perfect. It's in the Hookean region, obeying the law, snapping back perfectly. But then it hits the limit of proportionality. The graph starts to curve. F equals kx isn't the rule anymore. Push it a little further and you hit the elastic limit. That's the point of no return. Go past that and you're in plastic deformation. The material is permanently stretched and damaged.
Okay, this is a super subtle but really important difference, and it's a favorite for exam questions. What's the difference between the limit of proportionality and the elastic limit? They sound similar, but they're not the same thing. The limit of proportionality is simply where the straight line graph ends and the law F equals kx fails. The elastic limit is where the material itself fails to spring back. And for a lot of materials, there's actually a small region where the line is curved, but it's still elastic. It'll go back to its original shape if you let go.
All right, you ready for the final boss? The bungee jump problem. This is the ultimate test because it pulls together everything we've just talked about. Force, energy, Hooke's law into one big challenge.
Okay, here's the setup. We've got a jumper, 70 kilograms. They're on a platform 50 meters high. The bungee cord itself is 20 meters long when it's just hanging there, and we know its spring constant is 73.5. So, the big question is, will they hit the water? We need to figure out the maximum distance they fall.
So, how do we solve this? The absolute key is the conservation of energy. All that gravitational potential energy the jumper loses as they fall has to go somewhere, right? It gets converted into elastic potential energy stored in the bungee cord. This gives us our golden equation. mg times L plus x equals 1/2 kx squared. Now, if you plug in all the numbers, you actually end up with a quadratic equation. We won't grind through the math here, but when you solve it, you find that the stretch, x, is about 30.8 meters. Add that to the bungee's original 20-meter length, and you get a total fall of 50.8 meters. And since the platform was only 50 meters high, yeah, our jumper is definitely getting wet. Okay, let's boil this all down. If you're heading into an exam, this is your cheat sheet. These are the absolute must-knows. The force and energy formulas, how to pull K and energy from a graph, the critical concept that X is always the change in length, and of course the big one for problems like the bungee jump, energy lost equals energy gained. This is your toolkit. So, there you have it. You've now got all the physics you need to analyze a bungee jump like a pro. But here's the thing. We've seen the math works out, but understanding the science is one thing. Actually taking that leap, that's something else entirely. What do you think? Would you trust the physics? Thanks for joining us.